Welcome back to the deep dive. Today we are skipping the introduction to textbooks and diving headfirst into the lab.
Straight into it.
Yep, specifically at the volatile intersection of large language models and one of chemistry's most complex challenges, chemical synthesis planning.
Huge one.
We've assembled a stack of sources that detail a really revolutionary framework. Your mission for this deep dive is to understand the blueprint for teaching a general-purpose LLM to speak chemistry fluently.
Something that's been a massive hurdle for a long time.
Exactly. And the core of this is how this novel approach overcomes the massive long-standing problem of chemical data scarcity to solve retrosynthesis.
And that data scarcity problem, it really can't be overstated. It is the central reason why traditional machine learning has sort of stalled out in molecular science.
It's just too expensive.
Chemistry is inherently expensive. Think about it. Getting reliable, perfectly labeled data on a specific chemical transformation, especially for these complex drug molecules, it takes huge resources.
And a lot of failed experiments, I imagine.
So many failed experiments. And traditional supervised learning, it absolutely relies on having tens of thousands of these perfect labeled examples. But for the newest, most complex targets, that data just doesn't exist yet.
So sidestepping data scarcity, that sounds almost too good to be true. If this LLM isn't fine-tuned on labeled reactions, where is it getting its chemical intuition?
That is the crux of the innovation.
How does it actually work?
They've introduced what they call the atom-anchored reasoning framework, and this framework allows a huge general-purpose LM1 trained on text, not molecules, to reason directly over molecular structures.
And crucially,
it does this without needing task-specific fine-tuning or demanding those massive labeled data sets. It literally anchors the LLM's internal chain of thought to the actual physical structure of the molecule.
Okay, let's look at the historical failures first, just to appreciate how big of a challenge this is. Why did LLMs previously fail so badly at direct chemical prediction?
Oh, they were simply not competitive. They failed because molecules, when you represent them as text strings, like smiles, they're just arbitrary combinations of letters to a general LLM.
It has no underlying concept of the chemistry.
None. Prior research showed that without specialized training, these big LLMs underperformed specialized chemical models by a staggering margin. We're talking over 40 percentage points in accuracy.
Wow.
Yeah. One study put it bluntly. When you ask these powerful models to generate reactions directly, they often solved only 1 out of 5 test examples correctly. They just couldn't connect the text to the chemical reality.
That's a brutal report card. It shows a total disconnect, really.
Yeah.
So how are they even being used at all before this new method came along?
Their use was highly indirect. So chemists might use an LLM to enrich the chemical representations, generate a detailed text description of a smile string, which then feeds into a smaller specialized model. Or they'd use it to solve some chemistry math problem by having it generate code. But they were guides. Enhancers. They weren't the engine doing the actual retrosynthesis, which is, working backward from the product to the ingredients.
Here's the fascinating paradox, then. The core chemical structure, the molecule itself, is still represented by a text string, the smile string.
Right.
So if the LLM just reads text, how do you force it to anchor its internal logic to the structure instead of just, the sequence of letters?
And this is the genius of the innovation. They use smiles, atom maps. In a traditional smile string, which just describes how atoms are connected, they add unique numerical identifiers, little tags to every single atom.
Like a label.
Exactly. So the LLM is then required to explicitly use these atom tags like C.12 or N.14 in its step-by-step reasoning process.
I see.
By forcing that rule, the reasoning becomes structurally grounded. The LLM can't just hallucinate a generic reaction anymore. It has to confirm the specific atoms involved in breaking and forming bonds. It's basically mimicking how a human chemist follows a reaction on a whiteboard, atom by atom.
That makes perfect sense. It's like giving the LLM a legend for its own text. So let's look at the actual operational blueprint. It's a 2-stage process. We'll call them stage 1, position, and stage 2, transition.
Perfect. Stage 1 is the position model. Its formal name is the zero-shot position model, which means the LLM is working completely cold zero examples.
Okay.
Its only job is analytical. It looks at the structure, it identifies the key fragments, and critically, it finds all the potential disconnection candidates. These are the spots where the molecule could best be broken apart.
So stage 1 figures out where the reaction should happen and why that's the best place to break the molecule just based on high-level chemical logic.
Exactly. Then stage 2 is the transition model. This stage takes that positional info, the where, and, guided by a few examples, it predicts the actual chemical transformation and what the final reactant molecules need to be.
Splitting it into position, the where, and transition, the what, seems really smart. But doesn't that risk solving the wrong problem perfectly? What if the position model suggests a site that's plausible but, ultimately inefficient?
That's a very valid concern, and that's why the whole framework is built on strategic prioritization. It's designed to prevent those exact dead ends.
How so?
The strategic goals, built right into the LLM's prompt, they define what makes a good synthetic route. Think of it like a game of molecular chess. The goals are structural simplification.
Getting it down to simpler pieces.
Right, readily available pieces. Then reaction robustness, making sure the forward reaction is reliable, high yield, safe. And finally, strategic construction, which is about building the core molecular scaffold efficiently.
And how do they force the LLM to prioritize one plausible disconnection over another?
By assigning a numerical retrosynthesis importance score from 4 down to 1. This is where the human chemical intelligence is explicitly coded into the AI's reasoning.
So what's a 4?
An importance 4 score, that isn't a simple pawn move. It's the queen's gambit. It's a high-impact strategic move. It's for things like major ring-forming reactions or disconnections that convergently connect major fragments.
Meaning you're linking two big complex parts of the molecule together.
Exactly. You're drastically simplifying the whole process, making the route shorter.
And the lower scores, what would be an importance 1?
Importance 1 is generally for tactical but necessary steps, like protecting group analysis. For instance, the model might suggest removing a common protective group, like a Bachamine deprotection, in the forward synthesis.
So it's vital for making the chemistry work, but it isn't the big strategic bond formation.
Precisely. That clarity, strategy versus tactics is what turns the AI from a prediction engine into a real planning tool.
Okay, let's look at the results. How well did this position model actually do at finding those reaction centers?
On the rigorous USP250K evaluation set, it achieved remarkably high accuracy. Across the top models, the rate for finding a chemically plausible reaction site was consistently at or above a 90% partial match.
90%.
Gemini 2.5 Pro scored, I think, 91.87%. This means in over 9 out of 10 cases, the LLM successfully identified a defensible starting point for a reaction. That's a huge win, because it immediately narrows the search space for a chemist.
That is impressive. Okay, now moving from the where that 90+% accuracy to the what of the transition model.
Right.
How did it do at translating that location into the final reactants?
So the transition model showed that performance scaled logarithmically with the size of the LLM at first,
Right.
which confirms that having a large knowledge base is essential. But then it plateaued, meaning size isn't everything.
Right.
But here is the single most critical finding from the whole study. It comes from the ablation studies, where they isolate the factors contributing to success.
Okay, let's focus on that. What was the dominant factor?
The importance of chemical context was just immense. Performance dropped dramatically by about 50% for unknown reactions when tested zero-shot versus when they were tested few-shot, where the model got up to 5 ideal examples of that reaction class.
Wait, a 50% drop just by removing 5 examples?
Yeah.
That seems huge. It means the LLM's vast general knowledge just isn't enough on its own.
Exactly. The prediction of the reactant set suffered severely. It dropped from an achievable accuracy of about 75% down to around 30% when no examples were provided.
Wow.
This is the crucial insight. The inclusion of those few-shot examples proved to be the dominant factor for success. A detailed prompt alone got accuracy to about 59%, but adding just those 5 examples, that was way more effective. It raised the best combined accuracy all the way up to 81%.
So we're learning that the few-shot examples aren't just minor nudges. They're like critical chemical anchors.
That's a perfect way to put it.
They define the specific mechanism and scope that the LLM should be reasoning about for that particular molecule.
Precisely. It lets the model use its reasoning engine in a specific chemically valid context instead of just relying on its general knowledge, which, lacks the fine-grained reactivity details you need for complex retrosynthesis.
This raises a really important question then. Does this framework hold up in the real world of drug discovery? Or does it only work on clean academic benchmarks?
A critical check for any new AI in science, right? The researchers validated it not only on standard public datasets, but also on 5 expert-validated drug discovery
Oh,
molecules.
real-world stuff.
Absolutely. Complex compounds like LEI 515 and DH376, which had been successfully synthesized and published in high-impact journals, this is the ultimate stress test.
And the results.
Extremely strong. Looking at the averages across these real-world molecules, the model hit a 90.5% success rate for identifying chemically plausible disconnections. But, and this is more important for a bench chemist, it got a 77.8% success rate in predicting steps that could realistically work in a laboratory setting.
Hold on. 77.8% success on a reaction that will realistically work in the lab. That's a massive win.
It is.
It means for every 4 proposals the AI gives you, 3 are highly likely to proceed without major issues. That could drastically cut down on failure and time. Can you give us a specific example of the model's reasoning?
Certainly. Let's look at that complex molecule LEI 515. For a crucial step, the model identified the C12N.14 disconnection for an amide conversion, and it assigned this a high priority and importance 4 score.
And what did the LLM actually say? What was its rationale?
The rationale was explicit and deeply chemical. It stated that this was a high-impact convergent disconnection, meaning it links 2 large, distinct fragments, which drastically simplifies the overall challenge. It also explicitly noted that the forward reaction amide coupling is an extremely robust and reliable reaction type. It was reasoning like a seasoned synthetic chemist.
Did the reasoning stop at just finding the solution, or did it anticipate problems?
It anticipated problems. The reasoning explicitly flagged a key chemoselectivity concern.
What kind of concern?
It noted that for a later step, an N-arylation, there's a regioselectivity issue between 2 different nitrogens in a piperazine ring. And it concluded by suggesting the potential need for a protecting group on one of them to make sure the reaction goes exactly where you want it to go.
That level of foresight, identifying a tactical protective step needed downstream, is exactly the kind of critical thinking that defines a world-class chemist's planning.
So what does this all mean for you, the listener? Well, the framework provides an explainable rationale for its predictions. It ensures validity across stability, chemoselectivity, stereochemistry. It immediately defines and intelligently navigates the search space for synthesis planning. It turns the LLM from a prediction tool into an intelligent partner.
In essence, we've moved from teaching the LLM vocabulary to teaching it grammar and structure. You can now predict not just what happens, but why it should happen. This is the clearest blueprint we've seen yet for applying LLMs to these data-scarce problems in science.
And that explainable rationale is, I think, the broadest and maybe the most valuable contribution. Knowledge is most valuable when it's understood and applied, right?
Right.
This framework's ability to generate chemically grounded, explainable rationales is arguably as important as the prediction itself. It injects a vital layer of critical thinking into the machine's output, pushing us towards reliable, high-yield discovery.
This deep dive really confirms a significant shift. LLMs are moving past just processing chemistry as strings of text. They're now engaging in structure-anchored, complex chemical reasoning, opening up vast new pathways in drug and material discovery.
It's a fundamental change.
But let's leave you with one final thought to mull over. Since those few-shot examples prove so dominant in determining the model's accuracy, drastically raising its performance, how might the quality and diversity of just a handful of expertly selected examples fundamentally shape the ethical and practical boundaries of what LLMs are chemically allowed to synthesize? What happens when those few hand-picked examples limit the LLM's imagination, or maybe bias its priorities toward the familiar, potentially cutting off paths to true molecular novelty? That's all the time we have for this deep dive. We hope you feel thoroughly informed and ready to think critically about the future of AI in the lab.